Hello everyone, welcome to the another session of operating system theory. So let us move on to the new chapter here, memory management. And in this chapter we are going to see some kind of memory management techniques and how the operating system manages the memory here for the efficient execution of all the processes. Okay, so before we go into the deep, let us have a general idea about how the processes or program runs in the memory. Okay, so see, for example, like we have a secondary memory here. Okay, and this is the, let us say, a main memory. Fine, and we have something called as the CPU here. Okay, this is CPU and this is main memory, and this is the secondary memory. Fine, so you can say it as a disk here, hard disk. Fine, so program must be brought from disk here into the main memory and placed within some process here for it to be running state. Okay, why? Because CPU has access only to the main memory. CPU cannot access directly to, CPU doesn't have any access to directly to the secondary memory. The CPU is the one, it has access only to the main memory, or it has access to some small memory blocks here called as the registers. Okay, so main memory and the registers, these are the only storage units CPU can access directly. Okay, and it's more efficient. Like, see, if CPU needs any kind of information or any data or instruction, it doesn't have to go all the way to secondary memory. It looks into the main memory for the execution of that process. So basically, for a program to run, the program must be brought in from the secondary memory to the main memory. Is it clear? Okay, so here we go. So program must be brought from disk into memory and placed within a process for it to be run. Okay, and you see, CPU can access directly only to the main memory and the registers. These are the only storage that CPU can access directly. Okay, there is also one kind of a small memory here, cache memory, which is a faster memory which sits in between the main memory and the CPU registers. Okay, so we have something like registers, cache memory, and the main memory. So CPU can access directly to these memory chunks for the for the process to run. Okay, so how a process sits in to the main memory actually here. So basically we have something like some set of processes here. You see, this is the main memory, and when the program is, system is started, these memory area, some of the memory area will be occupied by the operating system itself. Okay, and the remaining will be left for the user processes to run. Okay, so the processes comes in from the secondary memory and sits in here in the main memory here. Okay, so where these processes are going to be occupied is being registered here as, it is stored, the address is stored is something like base register and the limit register. See, for example, like this process is having a base register of something like 30,000, something like 300040. Okay, and how long this process can occupy, that is the that is stored in the limit register here. Fine. So basically these two registers will define the logical address. We will talk about this now for the what exactly is logical address and physical address. So basically you see the logical address is something like which sits in the secondary memory, and the physical address is something like which is in the main memory. Okay, we will talk about that. Right. So next here there is something called as an hardware address protection here. What is that? See, basically the CPU generates some kind of logical address here, an address, and this address must be checked with the base address over here. Okay, and it also checks in for the limit address. Suppose that accidentally, for example, like over here, if CPU generates an address which is beyond the current execution of the process, suppose that if it is generating some wants to retrieve the value or something, some information, and it has given an address which sits in from the other process, then it is going to be an error here. Fine. So in that case, before giving the address into the memory, CPU, the operating system will check with the address generated by the CPU. Like if it is not in the limits of that process, if the address generated by CPU is not in that limits, then it will create a trap here. Trap means an interrupt. Fine. So basically this was with the user mode now. So now the operating system will take care of that particular address, the process now, and will try to figure out the things here. Okay, so basically this is a kind of protection here. Okay, all right. Okay, so again, see, basically before I go here, let us see what is this logical address and physical address. See, logical address is something like it's generated by the CPU. CPU generates some kind of address and it is referred to as virtual address. Okay, and the one if you look at here, the one sits in here in the memory address, main memory, is something called as the physical address. So memory unit sees this address. Memory unit does not know the logical address. It knows only about the physical address over here, wherein the process is sitting here in the main memory. Clear my point? So see, basically if a process is stored something over here in the secondary memory with some address 0 to something like some 500 here. Okay, and this process is loaded over here. Fine. So how is it going to be loaded into this main memory? Where it's going to be stored here? This mapping can be done at some different stages here. Clear my point? Suppose that it may not set it from 0 to 500. The address may not be the same here. Okay, getting my point? So it may be something like starting from some particular address, let us say some 12,000, let us say. Okay, and that 12,000 is the base address over here. That will be considered as the base address. Based on that base address, the address of each chunk here will be calculated. I mean the instruction and the data will be stored here. Okay, and CPU generates what? It generates the logical address, and this logical address will be given to the main memory, and main memory does not see what is this logical address. This has to be mapped to this physical address. That is what we call it as the binding here, the address binding. Clear my point or not? Let us say I'll explain you with some kind of example here. Say for example, we have some list of students. Okay, some list of students. Okay, and everyone has something like some ID here, 1 2 3 4 okay, and 5. Fine. Now this is, I mean this is having some kind of addresses here. Now these students has to occupy the let us say an examination hall. Okay, and these 5 students has to sit somewhere from over here. Okay, fine. And this is starting from, let us say 1 0 0. Okay, so I mean this is going to be the base address here. I mean this tells you that where that program or process is going to be stored into the main memory, right? So suppose that if this is the student 1 and this is going to be stored over here at 100 plus 1, that is 101. So it will have something like a physical address as 101, and this will have a seat number as 102, and this will have something like seat address as 103, right? So CPU knows only the ID number. Okay, but the memory unit knows what it has, the what, the exam seat number. I mean 101, 102, 103. Fine. So this logical address generated by the CPU must be mapped to this seat numbers to identify the students here. Get my point? See, CPU knows only the ID numbers here, ID numbers of the students, but it doesn't know where these students are sitting in the exam hall. Okay, so I mean what is this exam hall actually? It's nothing but the main memory. Get my point? So these addresses, logical addresses, must be mapped to some location in the main memory, and that is what we call it as the physical address. Clear my point? Okay. Right. So memory management unit, like this one, you see, as I told you, when this logical address is being given to this main memory, okay, but this logical address is not known to the main memory. This has to be mapped to some physical address over here. Fine. So that mapping of that address is done by the memory management unit. Memory management unit, what it does, it maps the logical address to the physical address using some relocation register. Okay, clear my point? Let us see that with the help of a diagram here. See, CPU has generated some logical address here, 346. All right, and this must be CPU doesn't know where is it stored in the main memory, this 346. Fine. So what do we have? This is relocation register. This is nothing but the base register, and where this the process is starting from in the main memory, and the process is starting from 14,000 here. So using this base register, the relocation register, the logical address will be mapped to the physical address. That is 346 plus 14,000 will be mapped to as something like 14,346. Got my point? See, for example, like I told you the example of the students and exam hall. See, this is the ID of the student, okay, and this students has to sit in the exam hall, okay, but we don't know, where they are sitting in the exam hall, we don't know. We just know the IDs of the students, fine. So using that, we just know that where these students are sitting, the starting address, we know it, okay. So using that starting address of that exam hall, we are trying to find out the address of each and every student here, where these physical address of that particular students, okay. Suppose that let us say here 14,000 is the starting address of that particular student, okay, and we want to know the address of this 346. So this 346 will be simply add to this 14,000 and we get that particular student address, and that will be mapped over here, and that information will be given to the CPU for execution. Clear my point? All right, moving on to the topic swapping here. See, basically we will talk about this in detail. There are some kind of situations wherein a process has to be swapped out of memory to the backing store and then brought back into memory for continuing its execution. See, you will find out this something like a view of how swapping in is done here. See, this is the main memory and the processes are sitting in here, okay. Say for example, like if process is executing in the main memory and for some reason it has to be swapped out into the backing store, yani some hard disk here, fine. So this needs to be swapped out, okay, and swapped out means there must be some switching here, yani the process has to stop here, some information has to be swapped in from the main memory and it has to store into the backing store here, fine. And any such another process can swap in into the user space, fine. So this kind of rolling out of the process and rolling in of the process is what we call the swapping here, okay. This is also called roll out and roll in, fine. A process can be swapped temporarily out of main memory to a backing store and then brought back into memory for continued execution. Clear? Okay. We will see when this swapping occurs in the coming topics here. Okay. All right. Contiguous allocation. See, basically you see we have seen that the processes, the program has to come in from over here. Let me okay. Now let us see here. We have this secondary memory, like we were talking about this contiguous allocation, right? So contiguous allocation is actually one of the memory management technique for allocation of the memory allocation scheme, wherein like the process has to come from here, loaded from secondary memory into the main memory. Okay, so basically the process that is loaded from main memory into the from secondary memory to main memory, it will be in the sequential manner, any contiguous section here. And for suppose if it is process has to sit in for some contiguous memory blocks here, yani P1 cannot sit here and cannot sit here. It has to sit over in the continuous fashion, yani all this has to be occupied over here. Okay, like this partition can be something like 2 MB or whatever, like, okay, get my point? So the process, suppose that another process is loaded into the memory, fine, so this will be stored over here, something like this. Okay, suppose if another process is loading here, it's something like it's gonna take the P3 over here. So I mean the process has to be loaded into the memory in contiguous manner, in contiguous fashion here. See, each process is contained in contiguous section of memory. Okay, get my point? And here in this contiguous allocation, basically we have this main memory divided into, I mean follows two partitioning schemes here. One is the fixed partition scheme and the other one is the variable partition scheme. Here in fixed partition scheme, what happens here is before itself this main memory will be configured to have the limited number of partitions, yani the partitions will be fixed. Okay, see here, this is the RAM here, the main memory, and some of the part is occupied by the operating system, and this is called low memory, and this the other one is termed as something like high memory, which is left for the user processes. This is user space. Got my point? Now this user space is going to be divided into some fixed number of partitions. Okay, suppose that if I have something like here 4 partitions here, fine, so only 4 processes can load into the main memory, not more than 4 processes can be loaded at the same time in this main memory. So that is the disadvantage of the fixed partition here. It is like it is bounded to the number of partitions. Get my point? Yani multi-programming, I mean there is something called as a degree of multi-programming here. This will not be achieved. Any degree of multi-programming means if more programs are running at the same time, the higher degree of multi-programming. And a CPU wants to execute as much as processes over here, I mean so that more programs can be run concurrently at the same time. That is what we call it as the multi-programming concept here. So if you look at here, I mean the degree of multi-programming is bounded here. I mean you can run only the fixed number of partitions, fine, so it is bounded to degree of multi-programming is bounded to the number of partitions here. Okay, what is it? This is fixed partitioning scheme. This is fixed partitioning scheme. Get my point? Suppose that this is like P1 is 2 MB and be different size, please. It's nothing like partitions must equal. It can be equal or it can be different sizes. Something like this is 2 MB and this is 2 MB. Some 2 units here. I'm just saying here megabytes here. Okay, some 2 units of memory, 4 units of memory, and 2 units of memory here. Clear my point? Suppose that let us say this process P1 sits in here from, I mean it's loaded from the secondary memory and it's stored here. Okay, and it's taking P1 has having something like only 1 MB. 1 MB of space. Okay, so what happens here? Only 1 MB will be occupied. Okay, and P2, I mean this particular space will be wastage, right? But this partition is having how much space? 2 MB space, but the process size is what? Only 1 MB. So the remaining 1 MB cannot be used here, is wasted. Get my point? The process P1 has loaded into the main memory here, and it's having only the size as 1 MB. Okay, and I think only the 1 MB. So now this has to sit into this partition P1. Okay, and this partition size is what? 2 MB, and the process size is out what? For 1 MB. So only 1 MB of space will be occupied here, and remaining 1 MB will be wasted here. Okay, so this wastage of space is what we call it as internal fragmentation. Okay, that is unused memory, that is unused memory which is internal to this partition. Okay, so this is one of the drawback of this contiguous allocation, that is internal fragmentation. Okay, there is another type of external fragmentation called external fragmentation, another disadvantage. We will talk about that. Okay, now before we go into that, let us see another type of partitioning scheme, that is variable partitioning scheme. We have fixed and variable partition scheme, two things. Okay, so what happens here in variable partition scheme here is the number of partitions are not fixed. The number of partitions are not fixed, unlike this fixed partition scheme. What happens here is it dynamically allocates the partitions to the process according to the process coming in to the main memory. Get my point? So suppose that okay, so let us say here in variable partitioning scheme there is no limit to the number of partitions here. Like as a process is arriving in here, a partition will be generated, something like this one. Let us say over here. Okay, first process has come in and it's say, let us say it's P1. Okay, and it's taking something like 2 MB. Fine, and second process comes in and it's taking something like 4 MB here. All right, and let us say I call it as P2 here, and let us say some more process comes in. This is something like P3. Okay, and another process, this is something like P4, and let us say P5 also comes in. Okay, let me say this P3 partition is 1 megabyte, and let us say this is 2 units of memory, let us say. All right, so as soon as a process comes in, I mean the partition will be allocated dynamically here. Okay, so this fixed partition is something like static number of partitions here. The number of partitions are static, and in variable partitioning the number of partitions are dynamic according to the arrival of their processes here. Okay, so say for example these processes like P1, P2, P3, P4 and P5 has loaded into the main memory. Okay, suppose that P1 has completed its job. All right, P1 has completed its job, and this slot is free now. Okay, now this slot is free, and this free slot is what we call it as whole. This free slot is called as whole. Okay, and let us say this P3 has also, let us say, finished its job. Okay, so there are something like available slots and free slots. Okay, let us say this P2 is still working, it's in the main memory, and P4 is in the main memory, and P5 is also in the main memory. P1 and P3 has finished its job and it has created some space. Okay, they have left here, so it has created some free space here. Suppose that another process P6, another process P6 wants to come into the main memory. Okay, and the size of this, let us say P6 is, let us say, 2 MB. Fine. So basically what is happened, it will look into the available free slot that can accommodate here. Okay, what is being done here, this P6 will be, we'll look for any free slot, any hole that is large enough to hold this process. Get my point? It will look for the free slot that is large enough to hold this particular new process. Get my point? Suppose that, okay, if it is like P6 is 2 MB, this P6 is going to sit in over here directly, no issues. Say for example, now if P6 is having 3 megabytes of space, okay, can P6 sit in here? No, it's not possible. Why? 2 MB space. But you see, we have 1 MB space also over here. Here 2 MB and 1 MB here. But still we have 3 MB of space, but this process P6 cannot be accommodated. Why? Because this is contiguous memory allocation. Yani the process has to sit in contiguous section. Yani part of this will not be stored here and part of this will not be stored. Okay, even after having the enough memory for the process to load into the main memory, we cannot load that process here. Okay, so this type of problem is what we call external fragmentation. What is it called? External fragmentation. And this is like something like we have enough memory to satisfy the request, but the available space, we have the available space, we have enough memory here, but to satisfy that request, but the available space is not contiguous. Okay, we have 2 MB here and 1 MB here, so this process cannot sit in over here. So this type of problem is what we refer it as external fragmentation. Okay, what is internal fragmentation? If there is any free space occupied by the process that is internal to partition. Okay, suppose that P2 is having of size only 3 MB, but this partition scheme, this partition is having 4 MB. So what happens here? Only 3 MB has been occupied, but this 1 MB is free, is wastage. Okay, this is internal fragmentation. Okay, hope you understood this. Okay, all right, so we have this first fit, best fit and worst fit allocation strategies here. As I told you over here, when a new process is coming in from the secondary memory and that is being loaded into the main memory, okay, and this process memory will be checked in here, and it tries to find out the hole that is large enough to hold that process. Okay, so to find out that freely available space or hole, we have 3 different strategies here. What is that? First fit, that is allocate the first hole that is big enough. Yani it will try to search in starting from the main memory, okay, and it tries to find out the first hole that is large enough to hold that process. If it finds first hole, okay, then the process will be allocated over there. Okay, this is first fit strategy. What is the other one? Best fit. And if best fit is, it will search from the starting here, and if it will not allocate directly with the first hole here, first memory space. Rather than it searches for the holes which is having an optimal space, yani smallest space that is large enough to hold that is big enough to hold that particularly that process, yani smallest leftover hole. Suppose that let me tell you here, this hole is 2 MB and this hole is 1 MB. Fine. Suppose that a process with 1 MB is coming in. Okay, so what is the first fit strategy does? It looks for the first hole which is of size 2 MB. Directly it will allocate the space here without considering that, okay, 1 MB is wastage here. Okay, that is first fit strategy. Wherein best fit, what it does, it looks for the optimal smallest fit that is large enough. See, 1 MB can fit here, but it looks for more free spaces. Okay, suppose that it is having 2 MB here, okay, and here we have 1 MB, and this 1 MB process can be allocated here. Okay, so it tries to find the best fit for that process. Okay, that is what we call best fit. Allocates the smallest hole. Here hole is referring to the free memory, please. Okay, all right. And worst fit is allocates the largest hole, yani largest leftover hole will be allocated to that process. Clear my point? These are the three different techniques here. Okay, all right, so this is what we talked about, this external fragmentation and internal fragmentation. See, this fragmentation, external fragmentation, can be reduced by compaction here. What is that compaction? What we see here, the external memory, external fragmentation. See, we had enough space for this P6 to accommodate here. We had here 2 MB and here 1 MB, right? We had here 2 MB and we had 1 MB. Fine, but this was not contiguous, right? So this external fragmentation problem can be reduced by compaction. What it does, it pushes in the memory blocks here to make it contiguous over here. Okay, but that is not possible all the time. I mean this 1 MB will be pushed up and this will be brought into the next location. Fine, so here changing of the memory blocks is not so efficient here, so compaction is not all the times possible. Okay, so this contiguous allocation technique is an older technique now. I mean, it's not used now, and it has some kind of disadvantages. That is the internal fragmentation, and the most important is the external fragmentation. Most of the we have the enough memory space in the RAM, but we cannot allocate the space for the processes here. Okay, so to avoid that, we have another to overcome that, we have another type of allocation scheme, that is non-contiguous allocation. Okay, in that we have two different methods. One is the paging, the other one is the segmentation. Okay, which is very important, please, examination point of view I'm talking about here. All right, okay, let us look at this paging technique of memory allocation. Like, it is one of the non-contiguous allocation method. Okay, so basically like the address space of the physical address space of the process can be non-contiguous here. Yani part of the process can sit in one location and the other part of the process can sit in another location. Yani it doesn't have to be in contiguous section here. See, in contiguous location, if P1 is starting from here, it has to completely sit in over here in the continuous fashion. But whereas in non-contiguous, some part of P1 can sit here and some part of P1 can sit here and some other at some other in the physical address space. But how is it possible? Here, see, and also you see this paging technique avoids the external fragmentation. That is, the problem of external fragmentation can be overcome here in the paging technique. Like you see, what was the problem of external fragmentation? Actually, we had enough memory, but the available space was not contiguous. Okay, so here, since we have the contiguous non-contiguous space, so that problem of external fragmentation can be overcome here. Okay, so what happens here is basically the physical memory is being divided into fixed sized blocks, and these are called frames. Okay, basically this is in the size of these blocks is power of 2, something like 512 bytes or 16 megabytes or 256 bytes or something like that. Its size is power of 2. Okay, and what other thing, the logical memory is also divided into blocks of the same size of that frame called as pages. Get my point? See here, and the physical address space here, fine, if it is something like this is divided, this one is divided in fixed size blocks. These are called what? These are called frames. These are called frames. Okay, this is the physical address space. Okay, and here for a process, particular process, we have the logical address space. This is also divided into blocks which is of the same size. Yani the frame size is having, suppose like 2 bytes, this page size must also be having 2 bytes here. Okay, so all the logical memory space of a process is also divided into equal size chunks. Okay, and this chunk is what we call it as page. Get my point? The process in the logical address space in the secondary memory is also divided into equal size of blocks called as the pages, and this one is also divided as frames. Okay, all right, and this paging also must keep track of all the free frames. Yani if some page is, process is loaded into the memory. Okay, suppose that if I say here this is like page 1, what happens here is I'll tell you by example here. So this is like page 0, page 1, or whatever it is, page 2, say, let me, this is 1. Okay, and let us say this block is 2, and let us say this block is 3. Okay, So for this particular process P1, this is one process P1, okay, it has 3 pages. All right, so when this process P1 is loaded into the main memory from secondary memory, fine, so this processes, I mean these pages can sit in any frame here, because the size of this frame is equal to the size of this page. Okay, so I mean if suppose that in contiguous allocation, what was happening, all these process has to sit in contiguous fashion, but here part of the process can sit in different manner, yani non-contiguous. Suppose that one page is, let us say it is sitting here, okay, the second page can sit in over here, and third page can sit in over here. Okay, so the process can be loaded here into the free frames of any, I mean in a non-contiguous fashion. Okay, fine. So now, I mean, how to know that this page, I mean the page 1 of process P1 is sitting in over here. So how to know that physical space here? So these frames also have the numbers here. Suppose that this is 0, this is 1, this is 2, this is 3. So all frames must be keep tracking here. I mean all the free frames, what are all the free frames, and what are all the frames that are occupied by the process. So these frames and pages must be kept in some table called as the page table here. Now this page table stores the information of the pages, wherein which of these pages are stored in which frames, which of the page of a process is stored in which frames. That kind of information is stored in page table, and this is the main thing which is required to translate the I mean logical to physical address. I told you, like CPU generates the logical address here, CPU generates the logical address of that process, fine, and it needs to find out the data instruction, I mean where this process is sitting inside the main memory. Okay, so with the help of that page table, this translation of logical address to physical address will take up. How is it going to be? You see, I mean this page table will be generated for every process, please. This page table is maintained for every process, and suppose that, let us see an example of P1 here. So how many pages we have here? 3 pages. So every entry in the page table is going to be for every page of that process. So let us say this is like 1 and 2 and third entry. Okay, so now this page table will keep track, like this one page 1 of P1 is sitting at which frame. So suppose that this frame is sitting in 0th frame number 0, it's sitting over here. Okay, and page 2 is sitting where? In frame number 2. Okay, this is stored here, and page 3 is where is sitting here, and frame number 4. So this information will be maintained in page table. Okay, so using this page table, the translation of logical address to the physical address will be done. Yani CPU wants to find out, I mean he knows only the logical address. Okay, the physical address is not known. I told you the example of that students, I mean CPU knows only the ID of that student, but CPU doesn't know where these students are sitting in the examination hall. Okay, so that is the actually the physical address of that particular students, where they are sitting in the main memory. Okay, that needs to be mapped, actually that needs to be translated from logical address to physical address. Okay, is that clear?